This is Muhammad Hawa. Good evening. Let's discuss some important properties of Fourier transform. The reason Fourier transform properties are useful is that they can save you time. For example, if you performed the Fourier transform integral and found out that the Fourier transform of rect of t is sinc omega over 2 pi. By the way, we solved this example. We had Fourier transform of a rect t over tau, and here I'm using a equal 1 and tau equal 1. This is the answer you're going to get, which is a very basic answer that I recommend you memorize. Once you memorize this answer, there is no need to keep performing integration to find the Fourier transform of variance of this signal. For example, if I say find the Fourier transform of a rect of t, or a rect of t minus t naught with a time shift, or find the Fourier transform of a rect of t minus t naught over tau where I have time scaling, you do not need to keep doing the Fourier transform integrals over and over. Just apply the Fourier transform properties you're going to learn in this video on the basic solution that you already memorized. You're going to get the answers for all the other variants of this signal. This is a big time saver. So we're going to go through a few of those important Fourier transform properties one by one, explaining each Fourier transform property, memorizing it, and also solving some examples. And let's start with the linearity or superposition property. Linearity or superposition states that if you know for two signals x of t and y of t that the Fourier transform of x of t is x of omega and the Fourier transform of y of t is y of omega, then the Fourier transform of a constant multiplied by the signal x of t plus b another constant multiplied by y of t is equal that constant a multiplied by the Fourier transform of x of t, which is x of omega, plus the constant b multiplied by y of omega, which is the Fourier transform of y of t. In other words, if you have a signal x of t in time domain and you multiply it by a constant, what will happen in frequency domain is that you will multiply the Fourier transform by the same constant. Also, if you add two signals in time domain, what you're going to do in frequency domain is add up their Fourier transforms. This is the linearity or superposition property of Fourier transform. The proof is quite simple. It comes from the integral definition of Fourier transform, because the Fourier transform of the sum ax of t plus by of t is the integral minus infinity to infinity of this signal ax of t plus by of t e minus j omega t dt. Notice that integration can be split over addition, so I can split this integral into two integrals. This integral of the signal x of t multiplied by the exponential e to minus j omega t dt plus this integral where I multiply y of t by e to minus j omega t dt. I can take the constants b outside and a outside. This is the Fourier transform integral for the signal x of t, which means it is x of omega. And this is also the integral definition of Fourier transform of y of t, which gives you y of omega. The proof, as you can see, is quite simple and comes directly from the integral definition of Fourier transform. That's why I'm going to skip doing the proof for every property that we're going to go through and rather concentrate on giving you some examples to show you how to use those properties to your advantage. Before we go through this example, please keep in mind that superposition applies to any finite number of added signals. You could add 2 signals, 3 signals, 5 signals, 10 signals. It also applies to an infinite number of added signals if we have enough conditions to interchange the summation and integration. God willing, I'm going to show you an example later on where I apply this superposition property on an infinite number of added signals. However, for now, let's keep it simple. Our first example says, if you calculated that the Fourier transform of the unit step function is by delta of omega, that's an impulse, plus 1 over j omega. And you know this fact. Maybe you calculated the Fourier transform and you came up with this answer. Now determine Fourier transform of the signum function or the sine function. If you use Fourier transform properties, you do not need to do any integration, because the signum function sine of t can be written in terms of unit step function 2u of t minus 1. Please try to draw u of t, scale it by a factor of 2 and then subtract 1. You're gonna get the sine function. This is the sum of two signals, and I know the Fourier transform of the unit step function, which is this, and I know the Fourier transform of constant 1, which is an impulse, remember, multiplied by 2 pi multiplied by the constant. So using the superposition or the linearity property, I can say the Fourier transform of the sine function is equal the Fourier transform of 2 multiplied by u of t minus 1, which is equal to by the Fourier transform of this function. I took the scaling constant 2 outside, minus, I took the scaling constant minus 1 outside, the Fourier transform of the remaining part, positive 1. But the Fourier transform of unit step function is by delta of omega plus 1 over j omega, and the Fourier transform of 1 is 2 by delta of omega. This 2 multiplies by pi, multiplies by delta, cancels out with 2 by delta, and I'm left with 2 multiplied by 1 over j omega, which is 2 over j omega. Notice here I did not need any integration. I just used the property I memorized to get the answer so quickly. The second property we're going to discuss is called the complex conjugate property, which says that if you know the Fourier transform of x of t is x of omega, then the Fourier transform of the complex conjugate of x of t in time domain results in two changes in the frequency domain. First, you have to evaluate the complex conjugate of x of omega. Also, you have to introduce a reversal in frequency, which results from minus omega here. This is similar to how time reversal happens in time domain. Of course, this result applies for x of t, that is any general complex valued signal. However, in practice, we work with x of t, that is real valued signal. In this case, x of omega, the Fourier transform of x of t, is equal to the Fourier transform of x conjugate of t, because the complex conjugate of a real value is the same as the real value. The Fourier transform of x conjugate of t is capital X conjugate of minus omega, which means for real valued signals, I prove that x of omega is equal x conjugate of minus omega. Why is this significant? Because if x of omega is equal x conjugate of minus omega, this tells me that the magnitude of x of omega is the same as magnitude of x of minus omega, which tells me that the magnitude spectrum density of any real valued signal x of t should have even symmetry. And this result also tells me that the angle of x of omega is equal negative the angle of x of minus omega, which means that the phase spectrum density of any real valued signal x of t should have odd symmetry. We talked about this in an earlier video, but now you know that this results because of the complex conjugate property of Fourier transform. Another important property of Fourier transform is called time scaling or reciprocal spreading. It says that if you know Fourier transform of x of t is x of omega, then the time scaled version x of t over tau has a Fourier transform of x of omega so long as you multiply by the absolute value of tau here and the value of tau here. So if you divide t by tau in time domain, make sure to multiply by the absolute value of tau and multiply by the value of tau twice in the frequency domain. If tau is a positive real number, which is the case for periods of time like tau equal 5 seconds, then you don't need the absolute value here, and you could say the Fourier transform of x of t over tau is tau x of tau omega. I suggest you always write this expression and then remember to remove the absolute value if tau is a positive real number. By the way, this property can also be written like this, where we know that the Fourier transform of x of t, if you multiply in time domain t by a lambda, a constant, you have to divide by lambda twice in the frequency domain. Notice I divided by the absolute value of lambda outside x of omega, and I divided omega by lambda inside x of omega. This is an important property because you'll encounter time scaling on signals quite often. Instead of going through the proof, Let's solve this example. It says find x of omega, or the Fourier transform of x of t, for x of t equal 5 rect t over 30. Notice the time scaling here, and also notice the amplitude scaling here. Do I really need to do full integration here to find the answer like we did in an earlier video? The answer is no if you memorize the Fourier transform of the unit rectangular shape, rect of t, which is, by the way, sinc omega over 2 pi. Because you can convert this answer into your desired answer by applying Fourier transform properties. I will say Fourier transform of a rect t over tau, this is amplitude scaling. I'll use the superposition or the linearity property to take a outside the Fourier transform. And then I'll say rect t over tau has a Fourier transform similar to rect of t, but I have to multiply by tau twice. Multiply by absolute value of tau outside the sinc, and also multiply omega by tau inside the sinc. Remember, of course, there is a as well. So the final answer is a absolute value of tau sinc omega tau over 2 pi, which, by the way, we obtained using full integration in an earlier video. Now in my example, a is 5 and tau 30. So the Fourier transform of 5 rect t over 30 is a 5 multiplied by the absolute value of tau, which is 30 seconds, sinc tau, which is 30 omega over 2 pi, and that's my final answer. No integration necessary. In addition to evaluating Fourier transform so quickly, time scaling or reciprocal spreading has an important physical meaning. Let me read it first and then try to explain it. It says, compression of the signal in time domain results in expansion of its Fourier transform, meaning expansion in frequency domain. On the other hand, an expansion of the signal in time domain results in compression of its Fourier transform, meaning compression in the frequency domain. To show you what I mean, let's look at a visual illustration. I just calculated that the Fourier transform of x of t equal a rect t over tau, which is a single rectangular pulse with tau, amplitude a, is equal a tau sinc omega tau over 2 pi, which is this sinc shape with a bandwidth at the first null at 2 pi over tau. If I tell you, let's evaluate the Fourier transform of x of t, a rect t over 2 tau, which is also a rectangular pulse, but this time the pulse width is 2 tau. I expanded the pulse width. I stretched the pulse width in time domain. What is the answer? You're gonna say from the time scaling property, I have to multiply now by 2 tau here outside the sinc. See the 2 tau here, and also inside the sinc multiply omega by 2 tau, as you can see here. What are you going to get? You're going to get a sinc shape again, but because of this term, the first null happens at pi over tau. If you substitute pi over tau here for omega, you're going to get sinc 1, which is the first null. This tells you that the difference between the Fourier transform of this rect, which is sinc, and the Fourier transform of this rect, which is sinc, is that this sinc was compressed in frequency domain. So a time expansion, if you expand the pulse width, you're gonna get frequency compression. If you compress your signal in time domain, on the other hand, you're gonna get frequency expansion. This is a very interesting understanding of the reciprocal spreading or time scaling property. Please remember this property. Another valid way to look at this reciprocal spreading is that the wider the signal pulse in time domain, the smaller the bandwidth of the signal, which of course we evaluated from the frequency domain. So for this rect shape, because I have a wider pulse here, my bandwidth is smaller. And you can see because of our time scaling property, if this pulse width is twice as much as the pulse width here, the bandwidth here is half as much as the bandwidth here. This is an important result that not only applies to rect signals, but also applies to any general signal x of t, because the time scaling property applies for any general signal x of t. For example, look at this extreme case which we solved earlier. What is the Fourier transform of an impulse where I compressed my signal to the extreme? This impulse width is 0. I get a Fourier transform that is expanded to the extreme, you get constant. What happens if I expand my signal to the extreme? What is the Fourier transform of a constant A? The answer is x of omega 2 by A delta of omega. So you compress your Fourier transform to the extreme. This is called reciprocal spreading. If you compress time domain, you get frequency expansion. If you expand time domain, you get compression in frequency domain. The next property is time inversion or time reversal or time reflection, which can be easily obtained from the time scaling property. Notice that if you do time inversion, what you will get is frequency inversion in the frequency domain. Let me show you the proof. Remember that the time scaling property says the Fourier transform of x of t over tau is absolute value of tau x of tau omega. Now let's substitute tau here, -1. So we get x of t over -1, that's x of minus t, that's time reversal or time inversion. What is the answer? What is the corresponding Fourier transform? It's the absolute value of tau, that's absolute value of -1, x of tau, which is -1, multiplied by omega. So the Fourier transform of x of minus t is x of minus omega. So the final answer says if you perform time inversion in time domain, you're going to get frequency inversion in the frequency domain. Please memorize this result. And let's use it in an example. I gave you an example earlier to evaluate the Fourier transform of e to minus at u of t. And the answer was 1 over a plus j omega. Can we use this result to find the Fourier transform of e to positive at u of minus t, which is simply a time inverted signal of this one. Notice instead of t here, I have minus t, which means it cancels out with the minus. I get positive here. And instead of t here, I have minus t. Of course, solving this is so simple because I can use the time inversion property, which says that the Fourier transform of x of minus t is simply x of minus omega. Take every omega and replace it with minus omega. So I take this answer, 1 over a plus j omega, and I replace every omega with minus omega. So the Fourier transform of e to at u of minus t is 1 over a minus j omega. See how simple the calculation is if you memorize the Fourier transform properties. Another example, what if I say calculate the Fourier transform of e to minus a absolute value of t, which is simply two exponentials, one that is increasing when time is negative and one that is decreasing when time is positive. You can easily solve this problem if you break the signal into two parts. I say e to minus a absolute value of t consists of this first signal, e to minus a t u of t, plus this signal, e to a t u of minus t. This is a decaying exponential in the positive time, and this one is an increasing exponential in the negative time. We know the Fourier transform of this signal, which is 1 over a plus j omega. And we also know the Fourier transform of the second signal, which is 1 over a minus j omega. So the Fourier transform of the sum is the Fourier transform of the first one plus the Fourier transform of the second one. This is the linearity or superposition property. And I add up the Fourier transform of the first signal plus the Fourier transform of the second signal, I get 2a over a square plus omega square. That's the Fourier transform of the total signal, e to minus a absolute value of t. Another important Fourier transform property is time shift. Time shift could be to the right, so it could be time delay, or time shift could be to the left, that's time advance. The property says if the Fourier transform of x of t is x of omega, then the Fourier transform of x of t minus t naught, shift to the right by an amount of t naught, is the same as x of omega. You just have to multiply by e to minus j omega t naught, where t naught is the amount of time shift. Similarly, if you want the Fourier transform of x of t plus t naught, that's shift to the left by an amount of t naught, it's equal x of omega, the same original Fourier transform, but multiplied by e to positive j omega t naught. Typically, we write those two important results as one line. The Fourier transform of x of t plus minus t naught is x of omega e to plus minus j omega t naught. Please remember, this is actually two equations, not just one. What does this equation tell you? Remember that x of omega is a complex number. It has a magnitude and phase. because multiplying exponentials mean you add up the exponents, you're going to get as your answer absolute value of x of omega e to j angle x of omega plus minus omega t naught, which tells you that the magnitude of x of omega or the magnitude spectrum density is not affected by time shifts. On the other hand, the phase, the angle of x of omega or the phase spectrum density is affected by time shifts by adding plus omega t naught or subtracting minus omega t naught, which is a linear line in the frequency domain with a slope t naught or minus t naught. Let's solve an example to show you what I mean. Let's compare the Fourier transform for a rect t over tau, which we solved moments ago, versus the Fourier transform for x of t a rect t minus tau over 2 over tau. What is the difference between this one and this one? There is extra shift to the right in time domain by an amount of tau over 2. What is the solution? Well, we already know that the Fourier transform of a rect t over tau is a absolute value of tau sinc omega tau over 2 pi. Let's apply the time shift property, which says that due to this minus time shift, you have to multiply x of omega, this result, by e to minus j omega by the amount of time shift tau over 2. So the answer has the same magnitude, but there is an extra phase shift. In other words, delaying a signal by t naught seconds does not change its amplitude spectrum density, just its phase spectrum density by adding a linear line with a slope minus t naught. Let's draw this answer. This is a rect t over tau. Notice it is centered around 0. The magnitude spectrum density, absolute value of x of omega, looks like absolute value of sinc, and the phase spectrum density is equal by, if the sinc used to be negative, equal 0 if the sinc used to be positive, equal by if the sinc used to be negative, and so on. Remember, this has even symmetry and this one has odd symmetry. Now we shift our rectangular pulse in time domain to the right by an amount of tau over 2, so its value is a between 0 and tau. Still the pulse width is the same. I did not change that, I only shifted to the right. So what is the Fourier transform of a rect t minus tau over 2 divided by tau? Well, the magnitude spectrum density, as you can see, is still the absolute value of sinc, but notice that the phase spectrum density has now changed. There is this linear line of minus omega tau over 2 plus the original phase shift of by 0, and so on. This is the result of time shifts. What you get is the same magnitude spectrum density unaffected, but what you get is an extra linear line in the phase spectrum density. Alright, how about the other way around? Can we get a shift in frequency domain? The answer is yes. This is what we call the frequency shift property. It says if x of t has the Fourier transform of x of omega, and you multiply time domain x of t by e to j omega naught t, what you're going to get in frequency domain is the Fourier transform x of omega but shifted minus omega naught. Also, if you multiply in time domain x of t by e to minus j omega naught t, what you're going to get is x of omega plus this time, plus omega naught. Typically, we write this in one line, x of t e to positive negative j omega naught t has the Fourier transform of x of omega minus plus omega naught. Notice here the plus corresponds to the minus and the minus corresponds to the plus. This is of course a shift in the frequency domain. Minus omega naught is shift to the right and plus omega naught is shift to the left. Let's solve a couple of examples to see that this property is quite useful. This example says determine the Fourier transform of x of t multiplied by cosine omega naught t. By the way, once you study communication systems, they will tell you this is called amplitude modulated signal. It's a very important signal that you'll encounter in communication systems. What is the answer? Well, I don't need to do any integrals. I just need to expand cosine omega naught t using Euler's identity. So I want the Fourier transform of x of t cosine omega naught t, where cosine omega naught t is e to j omega naught t plus e to minus j omega naught t divided by 2. Let's distribute multiplication over addition, so we get x of t multiplied by e to j omega naught t multiplied by half, of course, plus x of t multiplied by e to minus j omega naught t multiplied by half again. This is the Fourier transform of addition, which is addition of Fourier transform. So I want the Fourier transform of the first plus Fourier transform of the second. Also from the linearity property, I can take the half outside and the half outside. What is the Fourier transform of x of t multiplied by e to j omega naught t in time domain? It is frequency shift. What you're going to get is x of omega, because this is a plus, you're going to get minus omega naught. Remember the half, of course, plus half, and then the Fourier transform of x of t e to minus j omega naught t is x of omega plus omega naught. So you get two copies of x of omega here and here, but this is shifted to the right by an amount of omega naught, and this is shifted to the left by an amount of omega naught. We say in communication systems that we moved our baseband signal into being a modulated or bandpass signal, but I'll keep this detail for more advanced courses. Let's solve another example. This is actually a result that I mentioned in an earlier video, and I told you I'll provide the proof later on. What if I say find the Fourier transform of x of t periodic signal, any periodic signal that repeats a certain shape or pulse b of t every t naught. This is a periodic signal with period t naught. It doesn't matter what periodic signal, any general periodic signal. What is the Fourier transform? I mentioned earlier that to calculate the Fourier transform of periodic signals, go ahead, calculate Fourier series, the complex exponential form, alpha n, and then convert that into Fourier transform by multiplying by 2 pi and introducing impulses. Is that the correct answer? Let's prove it. Since x of t equal repeat every t naught b of t is a periodic signal, it can be expressed using the complex exponential Fourier series form as the infinite sum n equal minus infinity to infinity of alpha n e to j n omega naught t, where omega naught is 2 pi over t naught. I know this from Fourier series. Now to find x of omega, the Fourier transform of the repeated b of t signal, we need to find the Fourier transform of the equivalent, which is the sum from minus infinity to infinity, alpha n e to j n omega naught t. The Fourier transform of the sum is the sum of the Fourier transform. But we already memorized that the Fourier transform of a constant like alpha n is 2 pi multiplied by the constant alpha n by an impulse delta of omega. What about when I multiply by e to j n omega naught t? That results in frequency shift. And instead of having an impulse delta of omega, I have to add minus n omega naught, which comes in from here. This is a shift in frequency domain. What did I prove? I proved that the Fourier transform x of omega of any periodic signal is the infinite sum of impulses, where the area of each impulse located at frequency n omega naught is actually 2 pi alpha n, where alpha n comes from Fourier series complex exponential form. Thus, for periodic signals, the Fourier series complex exponential form alpha n can be converted into the Fourier transform x of omega by multiplying each alpha n value by a factor of 2 pi and converting each discrete value alpha n into an impulse. This is a very useful and interesting result. As a special case of this result, let me give you a homework. Determine the Fourier transform of an impulse train. X of t equal repeat every ts delta of t. This is periodic signal where I repeat delta of t at 0, ts, 2ts, 3ts, 4ts, 5ts, and so on. So I get infinity impulses in time domain, which is known as an impulse train. The answer is that the Fourier transform of infinity impulses is infinity impulses. Hopefully we will use this answer in a later video when we talk about sampling. Our next property is called duality. It's a very important property of Fourier transform. It says if you know that the Fourier transform of x of t is capital X of omega, and you want to find the Fourier transform of capital X of t, it is equal to by small letter x of minus omega. What does that tell you? It tells you that if x of t is a time domain signal and capital X of omega is a frequency domain signal, you can interchange the two signals. You can take capital X and put it in time domain. You're going to get small letter x in the frequency domain, so long as you multiply by 2 pi and you do frequency inversion. As an example, if the Fourier transform of a rectangular shape in time domain gives you sinc in the frequency domain, then the Fourier transform of sinc in the time domain will give you rect in the frequency domain. Another example, if the Fourier transform of an impulse in time domain gives you constant in frequency domain, then the Fourier transform of constant in time domain will give you an impulse in the frequency domain. This is a very general rule. It's called the duality property. And it allows you to calculate the Fourier transform of so many signals. Like, for example, I say find the Fourier transform of sinc of t, and then find the Fourier transform of a tau sinc tau t over 2 pi. We know from our earlier examples that the Fourier transform of x of t equal rect of t gives me capital X of omega sinc omega over 2 pi. I think you should memorize this result by now. It's a very important basic result. Now that we know the Fourier transform of rect is sinc, what about the Fourier transform of sinc t over 2 pi? Notice I replaced omega with t, so that's capital X of t. What is the Fourier transform? It's the small letter x of t, but replace t with minus omega and multiply by 2 pi. So the answer is rect, replace t with minus omega and multiply by 2 pi. So the Fourier transform of sinc t over 2 pi is 2 pi rect minus omega. If you want to get rid of the 2 pi here, we could do time scaling. So take sinc 2 pi by t over 2 pi, which gives you sinc of t. This multiplication by this factor 2 pi here is called time scaling. What you have to do in frequency domain is divide by the absolute value of 2 pi and divide omega by 2 pi. This 2 pi cancels out with the 2 pi, and this minus disappears because rect is an even function. So rect of minus something is the same as rect of positive that something, which means the answer is rect of omega over 2 pi. I proved using Fourier transform properties that the Fourier transform of sinc of t is rect omega over 2 pi. I'll say it again. The Fourier transform of sinc of t in time domain is rect of omega over 2 pi in the frequency domain. What if you want the Fourier transform of a tau sinc tau t over 2 pi? That's very easy. Just employ the proper Fourier transform properties. For example, I'm going to use time scaling and evaluate the Fourier transform of sinc tau t over 2 pi. If I multiply by tau over 2 pi in time domain, I have to multiply by 2 pi over tau absolute value, and then I have the rect omega over 2 pi, but then multiply the omega by 2 pi over tau. And then let's do amplitude scaling, multiply by a tau outside the sinc, so we have to multiply by a tau outside the Fourier transform. This tau cancels out, this 2 pi cancels out, you're left with 2 pi a rect omega over tau. That's your Fourier transform of a tau sinc tau t over 2 pi. I did this Fourier transform of the sinc function, which gives you rect, to show you a visual illustration of the duality property. Here I show you two examples that we already solved. The Fourier transform of a rect t over tau is x of omega a tau sinc tau omega over 2 pi. On the other hand, the Fourier transform of a tau sinc tau t over 2 pi is equal to 2 pi a rect omega over tau. So the Fourier transform of rect gives you sinc in the frequency domain. On the other hand, the Fourier transform of sinc in the time domain gives you rect in the frequency domain. This is what we call duality. Notice that this function is exactly the same as this function. Instead of omega here, I have t here. This function is exactly the same as this function. Instead of t here, I have omega. The only difference is that I multiply by 2 pi extra here, and I have minus omega here, but because rect is even function, frequency inversion does not affect the answer. Please remember duality for Fourier transform. The next property is time convolution. If we have two signals x of t, and the Fourier transform of x of t is x of omega, and we have another signal y of t in time domain, the Fourier transform of which is y of omega. Then if I want to find the Fourier transform of x of t convolution y of t, the answer is x of omega, the Fourier transform of the first signal multiplied by the Fourier transform of the second signal y of omega. So convolution in time domain corresponds to multiplication in frequency domain. Instead of giving you the proof for this very important result, let me give you an example. For the signals x of t equal 2.5 rect t plus 1 over 4 and y of t equal rect t plus 1 over 4, find the Fourier transform of x of t convolution y of t. I want to solve this example using two techniques. In the first technique, I want to find z of tau, which is the result of convolution between x of t and y of t. And once I find z of tau in time domain, I want to find its Fourier transform, which is z of omega. In the second technique, I want to find the Fourier transform of x of t by itself, which is x of omega. And I want to find the Fourier transform of y of t by itself, which is y of omega. And then multiply x of omega by y of omega in frequency domain and see if I get the same z of omega that I obtained earlier. I think this will illustrate the property of time convolution much better than a proof. This example is actually an example that we solved earlier when we talked about convolution. This is x of t equal 2.5 rect t plus 1 over 4. This is y of t, which is rect t plus 1 over 4. And when you do convolution, because this rect has the same width as this rect, you're going to get as a result a triangle. Please notice that this triangle has a maximum amplitude of 10 and a width of 8, which means this is 4 seconds and this is 4 seconds, and is shifted from 0 to the left by a value of 2 seconds. So z of t, the result of the convolution between x of t and y of t, is a delta, triangular shape, delta of t plus 2, that's a shift to the left, divided by 4, and the amplitude is 10. By the way, this is the same as z of tau. I just changed tau into t to avoid any possible confusion when we do Fourier transform. So what is the Fourier transform of this z of t? What is the Fourier transform of a delta t plus t naught over tau? You could do an integral if you want to, or an easier approach is to start with the basic answer. Fourier transform of delta of t is sinc square omega over 2 pi. This is a very simple answer that you could memorize. Now use the linearity property and the time scaling property to get the Fourier transform of a delta t over tau equal a absolute value of tau sinc square omega tau over 2 pi. If you introduce a time shift plus t naught, you multiply by e to j omega t naught. That's the answer we're looking for. So z of omega, which is the Fourier transform of z of t, 10 delta t plus 2 over 4 is equal a multiplied by the absolute value of tau, 10 multiplied by 4, that's 40, sinc square omega multiplied by tau, which is 4, divided by 2 pi. Don't forget e to j omega t naught. The amount of shift is 2, so it's e to j 2 omega. That's the Fourier transform of the convolution result. In my alternative solution technique, I'm going to find x of omega, which is the Fourier transform of x of t, and y of omega, which is the Fourier transform of y of t. Remember, the Fourier transform of 2.5 rect t plus 1 over 4 is the same as the Fourier transform of a rect t plus t naught over tau, which I can evaluate from Fourier transform properties. So the answer for Fourier transform 2.5 rect t plus 1 over 4 is a multiplied by tau, that's 2.5 multiplied by 4, you get 10, sinc omega multiplied by tau, which is 4, divided by 2 by e to j. The amount of t naught here is a plus 1, so you get e to j omega. Similarly, the Fourier transform of y of t, which is rect t plus 1 over 4, is a multiplied by tau, that's 1 multiplied by 4, you get 4, sinc omega multiplied by tau, that's 4, divided by 2 by e to j omega t naught, where t naught is 1, so you get e to j omega. Let's now try to multiply x of omega by y of omega. Multiply this sinc by this sinc. You're going to multiply 10 times 4, that's 40, you're going to multiply sec 4 omega over 2 pi by sec 4 omega over 2 pi. You're going to get sec square 4 omega over 2 pi. You multiply e to j omega by e to j omega. You add up the exponents. You get e to j 2 omega. This is the exact same result we got for z of omega in our first solution technique. So we've seen in this example that if you find the Fourier transform of convolution between x of t and y of t, it's the same answer as the multiplication of x of omega by y of omega. This time convolution property is quite useful, especially when we talk about systems, because the output of a system will be calculated as convolution. How about the opposite, frequency convolution? This property says if you have two signals x of t with Fourier transform x of omega and y of t with Fourier transform y of omega, and you multiply the two signals in time domain, the Fourier transform of the multiplication is x of omega convolution y of omega in the frequency domain, so long as you remember to divide by 2 pi. This is a very important result that we will use later on when we discuss sampling, because we will be evaluating the Fourier transform of x of t multiplied by y of t, where y of t is an impulse train. But I'll keep this for a later video. The last two properties are differentiation and integration. In the time differentiation property, if you have x of t with Fourier transform x of omega and you find the derivative of x of t with respect to time, then the Fourier transform of the derivative is x of omega multiplied by j omega. And you could do the derivative n times, you'll multiply by j omega n times. For integration, if we have x of t with Fourier transform x of omega, then the integral from minus infinity to t of x of tau d tau is equal x of omega again, but this time divided by j omega, not multiplied by j omega. There is an extra term plus by x of 0 delta omega, which is an impulse around 0. Let me conclude this video by reminding you that instead of calculating Fourier transform every time using the Fourier transform integral you're familiar with, rather memorize the Fourier transform results for some basic signals. Typically, we organize this in a table, something like this, that lists the basic signals and their Fourier transforms, and then find the Fourier transform of any variant of such basic signals by utilizing the appropriate Fourier transform properties. A similar thing usually is found in Laplace transform. So if you have done this in Laplace transform, it's a similar thing for Fourier transform. Usually we summarize the Fourier transform properties also in a table, something like this. So if you memorize the table for the basic signals and the table for Fourier transform properties, you will be able to find the Fourier transform for many signals without any integration. Also, please remember that the Fourier series, the complex exponential form coefficients alpha n, have similar properties to those of Fourier transform, because you can think about them as the equivalent Fourier transform 2 by alpha n delta of omega minus n omega naught. So you can take some examples that I've given you in this video and convert them into periodic versions and calculate the alpha n's using Fourier transform properties. Thank you for your attention. See you in the next video.